तो ऑडियो वीडियो फाइन है। चलिए एक तो नए चैनल पे आप सब लोगों का स्वागत है भाई, जो भी मुझे देख रहे हैं। तो मैं उम्मीद करता हूं कि आपकी तैयारी जो है बहुत बेहतरीन चल रही होगी। एंड आज का जो सेशन है इसमें हम रिवाइज करेंगे पावर इलेक्ट्रॉनिक्स को, एंड द सेशन विल बी इन हिंदी एंड इंग्लिश बोथ. I mean, it will be the mixture of Hindi and English language, so that everybody can join with me and everybody can understand. So it will be a mixture of Hindi and English. Okay, so you can say the session will be in English, and I'll revise the entire power electronics, entire formulas and the concepts. I'll try to revise all those concepts also via those formulas. So I hope you'll enjoy the session, and let's start. So those who don't know me, my name is Ashu Sir, and I teach almost every subjects of electrical engineering, including power electronics, machines and power system, analog electronics. Okay, so every subjects I teach, so I'll teach you every subjects in the upcoming days. So don't worry, and we'll enjoy those sessions. I hope you will enjoy also. So before that, before going further, you have to subscribe our channel, and please like this session and press the bell icon so that you can get the notifications. Okay, तो चलिए दोस्तों, एंड ये सेशन आ रहा है हमारा हाउ टू टैकल गेट 2024 सिलेबस. सो 8th of November को you can attend this session also and you can get benefited. So let's start, guys. There are two sessions on power electronics for formula revision. So in the first session we'll discuss about two chapters: basics of power electronics and phase controlled rectifier. These two chapters are you can say 50% of the power electronics, because phase controlled rectifier is a large chapter and it will contain almost 2 to 3 marks, and that's why we'll cover that topic in today's session. So first we'll discuss about basics of power electronics. In the basics chapter, what you need to remember is Percival relation and some basic small formulas. What are those formulas? We'll discuss that. Okay, so let's start with this. Let's say I have an electrical circuit, and on this electrical circuit I have connected a voltage source with the value VST, and let's say there is a current source IST. VST and IST contain harmonic. I have written VST as V0 plus Vm1 sine of omega naught t plus theta v1 plus Vm2 sine of 2 omega naught t plus theta v2, and so on. So the voltage has harmonics, and you can say that this is the DC term, this is the fundamental term, this is second harmonic, and there are many harmonics. Similarly, the current also has harmonics. You can see that the current equation is written as I0 is the DC component, plus Im1 sine of omega naught t plus theta I1. Similarly, I have second harmonic Im2, this is Im2, or you can say N, whatever you call it, Im2 sine of 2 omega naught t plus theta I2, and so on. So there are harmonics in current also, and there are harmonics in voltage also. Now, what we need to calculate is the active power. How much average power this source is going to deliver this circuit. You should remember that formula. Active power or average power can be calculated using the Percival relation. So if I apply the Percival relation on this electrical circuit, or on this voltage and current, so the average power or the active power that is supplied by this source will be average power or active power that is supplied by the source will be V0 into I0 plus summation 1 by 2 Vmk into Imk into cos of theta Vk minus theta Ik. K represent harmonics, K from 1 to infinity. Now, many of you will think, what is this? I mean, what I have written in this formula? How to remember this formula? It is very easy to remember. This formula. Let's separate this. Let's open this summation. So if I separate this, if I open this summation, what I will get is PT average, or you can say the active power. Active power will be equal to V0 I0 plus 1 by 2. Let's put K equal to 1 here. So if I put K equal to 1, it will be Vm1 into Im1 cos of theta V1 minus theta I1 plus 1 by 2, let's take 1 by 2 common, plus Vm2 Im2 cos of theta V2 minus theta I2 and so on. And there are further more harmonics will be there. Okay. So now if you look at this formula, this is called Percival relation. So using the Percival relation, we are calculating the active power delivered by the source. This much of watt is the active power delivered by the source. And you have studied this Percival relation in signal system also. Now what this Percival relation is telling us is that you should remember that only the DC component of the voltage will combine with the DC component of the current to make the active power. It means in active power, same frequency terms will participate. If you multiply this component with this sine term, it will not participate in active power. It will not make average, the average power due to this component and this component will be 0. It will participate only the DC because it has 0 frequency, so it will participate with the 0 frequency component to make the active power. Okay, so you have to remember this. In active power, same frequency component will participate. Similarly, you can see that this is the fundamental term. The frequency is omega naught t and the maximum value is Vm1. So it will participate, it will mix with the current of the same frequency. You can see that here the current frequency is omega naught t. Again, same frequency is there. So Vm1 will mix with Im1. It will be multiplied with Im1 and cosine of theta V1 minus theta I1. And since you are using the maximum value, that's why you have to take 1 by 2 factor. If you are taking RMS value of current and voltage, you don't have to take 1 by 2 factor. Okay. So you have to remember like this. Similarly, the second harmonic 2 omega naught term. In 2 omega naught term, you can see that if you are taking Vm2, the second harmonic maximum value of the voltage source, then it will be mixed with the second harmonic only, Im2. So you can see that here I have written Vm2 Im2. Same frequency terms will mix to make the active power. Simple. You have to remember like this. Okay. And there will be one factor of 1 by 2 because you are using the maximum value. And you have to take cosine of this, cosine of theta V2 minus theta I2. Okay. So this way you can write the active power. I hope you understood. So this is my Percival relation. You have to remember that different frequency term will not participate in active power. Let's say I have an electrical network. Let's say I have an electrical network and here I have a source, a VST. And the VST is, let's say this is 5 plus 10 sine of 5t plus 30 degree plus 8 cos of 8t minus 45 degree. And the current IT. Let me show the current IT. IT is equal to 10 plus 3 sine 2t plus 8 cos of 5t minus 45 degree. Let's say the current is this and the voltage is this. We are taking this case. I have taken the random case. Let's say there is some network on which I have applied this voltage source and the demand of the network is this. This is the current demand. And I need to calculate what is the active power that is supplied by the source. How much power is absorbed by this network? We need to calculate that. So if you want to calculate the average power or active power absorbed by this network, then what you need to do is you need to apply the Percival relation. If you apply the Percival relation, you have to remember that the same frequency component of current and voltage will participate in active power. So the average power or the active power will be equal to, if I need to calculate the average power, then it will be equal to, since the voltage has the DC component and the current also has the DC component. So these two components will mix together, will multiply together and it will participate in active power or average power. So it will be 5 into 10. It will be 50 watt plus the next component. Now you can see that in current we have omega equal to 2 term. This term has frequency 2, but in voltage we do not have any term which is of frequency 2 radian per second. So you can say that this component will not participate in active power. It will not participate in active power. Now similarly, Here you can see that the frequency is 5 here, but in voltage we have a component whose frequency is 5 again. So you can say that we have same frequency, so they will participate in active power. They will participate in active power. This component will participate with this component. I mean, it will be multiplied with this and it will make the active power. Okay, so this will mixed with this. How it will be mixed, I'll discuss that. But before that, look at this component. It has frequency omega equal to 8. But in voltage source, we have the frequency 8 radian per second. But in current source, we don't have any frequency of 8 radian per second. So you can say that this will not participate in active power. So if I need to write the active power, then the DC component of current multiplied by the DC component of voltage, you have 50 plus, since we are using the maximum value of current and voltages, so I have to take 1 by 2. The maximum value of voltage is 10 and the maximum value of the current is 8 into cos of angle difference between, the difference of angle of voltage and current. But to find the angle difference, find the difference of the angle, what we need to do is, we need to convert these two quantities in same, like they should be both in sine or both in cosine, so that we can find the difference. Now this quantity is in sine term, this quantity is in cos term. So what we can do is, we can convert this in sine to find the phase difference. So if I convert this quantity into sine, it will be 8 sine of 5t minus 45 plus 90. So it will be 5t plus 45 degree. Okay. So this will be my, you can say, IT of, the component of current which has frequency 5 radian per second. So now this is in sine term and this is also in sine term. So the active power due to this component will be 1 by 2 voltage maximum value into current maximum value into cos of the difference of the angle. Difference of the angle is theta v minus theta I. Theta v is 30 degree and theta I is 45 degree. So what we can do is, we can take the difference, minus 15 degree. Okay. So this will be my active power. This much of watt will be my active power. I hope you understood this. Okay. This is called Percival relation. You have to remember this. Okay. So I told you how to calculate the active power. Now there is one more thing, apparent power. How to calculate the apparent power? The apparent power is VST RMS into IST RMS. You just need to multiply the RMS values of voltage and current. You can calculate the RMS value of this voltage and the RMS value of this current. And then you can multiply and you will get the apparent power. Let's calculate the VST RMS. Again, you have to apply the Percival relation for RMS value. So RMS voltage will be equal to, this is my voltage source. RMS value of this voltage source is DC component square plus 1 by 2 AC component square and summation. That 10 square is 100 plus 8 square is 64. You should know that. This is my VST RMS. Now we should also calculate IST RMS. So if I calculate IST RMS, then it will be equal to, again we can apply Percival relation on this equation, and it will be equal to root of the DC component square. DC is 10, so 10 square plus 1 by 2 AC component square, that is 9 plus 64. 9 plus 64. This will be my IST RMS. So we can multiply them together and we'll get the apparent power. So to find active power and apparent power, we must know the Percival relation. Now, if we know active power and apparent power, we can calculate the power factor. So power factor will be equal to, now we know that power factor will be equal to active power divided by apparent power, and we can calculate the power factor. It's very simple. Active power divided by apparent power. Or you can say the power factor is the factor of apparent power which is active. Factor of apparent power which is active. We can calculate the active power. But there are some students who think that apparent power square is equal to active square plus reactive square. Now this formula is not correct here. This is wrong actually. You cannot find reactive power like this, because here we have the harmonics in current and voltage. Whenever there are harmonics in current and voltage, or in any quantity, let's say harmonics in current only, but in voltage we have pure sine wave, but there are harmonics in current. Or you can say that there are harmonics in voltage, but current has only one component, sinusoidal component. If there is harmonics in any quantity, voltage or current, or if there are harmonics in both of them, then you cannot apply this formula. This formula is wrong. You cannot apply this. Why? Why this formula is not applicable? Because this formula is applicable only if the voltage source and the current source has one same frequency component. There should be only one component, sinusoidal component. Let's say this is the component in voltage source. So the same frequency component should be in the current, and it should be there should not be any extra component. There should not be any harmonics. Then only you can apply this formula. So it is a single frequency formula. Single frequency formula. Okay, you have to remember this. This formula is not applicable everywhere. Similarly, if we need to calculate the power factor, student, remember that the power factor is theta v minus theta I. Voltage angle minus current angle, and take the cosine of this. This is power factor. Now this formula is not applicable. This is again wrong. In case of harmonic, you cannot apply this formula. Why not? Because we do not know the phase of this VST and the phase of this IST. We do not know that. If we don't know that, how can we apply that? How can we calculate theta v minus theta I? Okay, so be careful about this. Whenever there are harmonics, these formulas are not applicable. Reactive power, you cannot calculate reactive power like this, because in case of harmonics, you have reactive power, but that reactive power is not in that plane, in P and Q. You can make the power triangle from here, na? This is my P, this is my Q, and this is my S. You know the power triangle, na? P, Q, and S. So they are in the same plane. P and Q are in the same plane. But in case of harmonic, you have one more reactive power, one more reactive component, which is at 90 degree to these two components P and Q. There is one more reactive component. That's why we cannot apply this formula. Okay. Anyway, I will discuss on this formula maybe in some other session, but be careful about this, and how to calculate the power factor you have to remember. This is the standard formula for power factor. Power factor is not this. This is not applicable everywhere, and you cannot apply this formula. Similarly, this formula is not applicable. Power triangle is not applicable also. Power triangle you cannot apply here. Okay. So you have to be careful about this. I hope you understood this Percival relation and how to apply this, because there are many situations in which we need that relation. Okay, let's say maybe we are charging some battery. Let's take an example. If we are charging some battery, the battery is like this. If we are charging some battery is a DC source, and I have connected a rectifier. Okay, I have connected a diode here, and this is a pure sine wave component. Now we know that the current will be like this. The current will be like this. Now can you tell me the power absorbed by this source? How much power this source will absorb? We know that the current is this. This is my IT, I naught T. This is my I naught T. Now, since this source is a DC source, so it will take power, it will absorb power only from the DC component of the current. Only from the DC component of the current. You remember this. Because the current has harmonics. Current is a periodic signal. Current, you can see that the current is a periodic wave. In periodic signal, we have fundamental term, DC term, and harmonics also, sinusoidal terms also. So those sinusoidal terms will not provide power to this DC component of the voltage. Only the DC component of the current will provide the power to this source, because it's a DC source. Voltage is a DC source. So you have to be careful while calculating the power absorbed by this source. Okay, I hope you understood this. Okay, so this relation is very important. Now let's come to the next thing. Next thing is distortion. How to calculate distortion in any wave? How to calculate the distortion in any wave? Look, any wave is made up of, let's say any periodic wave. I'm discussing about periodic wave. Let's say I have a periodic wave. In that periodic wave, I have a pure sine wave component, and there are harmonics also. Those harmonics, I call them distortion. They are creating distortion. That sine wave, I love that. Sine wave is the part which I love. Other than that pure sine wave, other than that fundamental sine wave, other than that, everything is distortion. So what I can do is, I can remove that sinusoidal from that wave, let's say I have a cup. In that cup, or let's say I have some bottle, or in that bottle, this much is water, I say. Okay, this much is water, and this is foam. This is foam, you can say. So the important thing is, I can, if I see the bottle, I'll see that this is full of, I mean, this is full. It will look like that it is, this bottle is full. But the important part is here only. Similarly, if you assume any wave, let's say the wave is like this, any periodic wave. Let's say the wave is like this. In this wave, we have a fundamental sine component, a fundamental sine term, and there are harmonics. Those harmonic represent the distortion. So what I want to do is, I want to calculate the distortion part. I want to separate out that distortion part. How to do that? It's very simple. Let's say this is the current signal. Let's say this is the current signal, IST. In that current signal, we have a pure sine component. So what I can do is, you can find the RMS value of this entire signal. In this RMS value, there is a participation of every frequency term, fundamental and higher frequency terms. Okay, there is a participation of every frequency term in this IST RMS. Now, what I want to do is, I want to find the RMS participation only because of harmonics. So what I can do is, I can subtract the RMS value of fundamental term. If I separate out the fundamental component, if I separate out the sinusoidal, fundamental sinusoid RMS, then what you will get? You will get the RMS value of the distortion. Okay, because you have separated the fundamental part. Okay, so the remaining part is the distortion. But RMS values are not subtracted like this. This is the main thing. RMS values are not subtracted like this. How to subtract the RMS values? Remember, RMS values are subtracted like this. You have to take the square of this and take the root of it. Then only you can remove. So this will be the RMS of the distortion. Okay. So this will be the RMS of the distortion. So you remember this point. Okay. This is IST distortion. IST distortion. This is my distortion. Okay. You have to remember like this. I mean, don't try to cram the formula. Okay. Try to understand what is the meaning of distortion. Distortion means, if you have a periodic wave, in that periodic wave, the fundamental sinusoid is the pure thing which I want. Other than that is the distortion. So what I need to do is, I need to find the distortion RMS. How to calculate the RMS value of the distortion only? You can calculate the RMS of the entire signal. From that entire signal RMS, you can subtract the RMS of the fundamental component. Okay. So what you left with is RMS of the distortion. Simple. Okay, so this is my distortion RMS of the distortion component. Now, this way we can find, this is the RMS of the total current IST RMS. Okay, this is my IST source current. So what you can do is, you can take the RMS of the source current and you can subtract the RMS of the fundamental component and take the root, and you will get the RMS of the distortion. Now, I need to find the percentage THD, total harmonic distortion. Okay. Sir, in this class, how many topics are discussed? In this class, only 2 topics will be discussed: the basics of the power electronics and the phase controlled rectifier. Those 2 topics I am going to discuss, and I am going to revise those 2 topics because there are so many things, there are so many formulas. So I want to revise those formulas. I hope you will enjoy. Don't worry. If you have studied power electronics, then surely you will enjoy this session. Okay. Now let's come to percentage THD. Now, what is this? What is the meaning of total harmonic distortion? Total harmonic distortion means, it is, you can say, it is the quality, it is the, you can say the purity, you can say. In any wave, how much percent is the purity? That we call distortion. THD, total harmonic distortion. Now, using the formula, you will understand that. Look, what is this? If I write it like this, IS square minus IS1 square divided by IS1. Now look, what is this? We know that we know about this. This is the total current RMS square minus the fundamental RMS square. It means this is the RMS value of the distortion part only, and this is the RMS value of the fundamental component only. So what you are doing is you are checking how much percentage is this distortion, what is the percentage of this distortion current of that fundamental. Let's say we have any wave, let's say we have this wave. In this wave, the RMS value of fundamental is, let's say, 10 ampere. Let's say this is the RMS value of the fundamental component. And let's say the total RMS is 15 ampere. Let's say the total RMS of the signal is 15 ampere. So what we can do is we can calculate the RMS of the distortion. So the distortion, RMS of the distortion signal is root of the total RMS square, which is 15 square minus 10 square. This is the RMS of the distortion. Now we want to calculate what is the percentage of this distortion. I mean, what the percentage value of this distortion. And if you need to calculate the percentage value, you must have some reference value, no? This is my reference value, IS1. How much percent is this distortion of this value? Of this value, how much percent is this distortion? You mean the fundamental component? Okay, you are calculating with respect to fundamental component. This is called total harmonic distortion. It is the measure of the quality. What type of quality you have? Okay, so this we call total harmonic distortion in current signal. Similarly, you can calculate the TSD in voltage signal also. If your voltage signal has harmonics, you can calculate the percentage THD in voltage signal also. So I mean, you have to remember these formulas by their names. I mean, don't try to cram this. Try to understand what this formula tells us. Okay, so similarly, you can proceed. Let's now discuss the crust factor. What is this crust factor? Okay, I don't remember. I mean, usually I forget this formula, and I don't require this formula either. Anyway, but let's say you are appearing in some state exam, then they can ask about the crust factor. So what is this crust factor? Crust factor is the IS peak. IS peak means what is the peak value of the current. Let's say this is my IST. So what is the peak value of this current? Divide by IS. IS means RMS value. IS means the RMS value. Peak value divided by the RMS value is known as crust factor. Okay, so you have to remember like this. I mean, if you forget it, no worries, because it's not required. They don't ask this term. Anyway, it is crust factor we call. Now let's discuss about power factor. Let's discuss about power factor a little. I mean, let's have some more discussion on power factor. Now, what is this displacement power factor? What is this displacement power factor? DPF. What is this? And what is this IS1 over IS? How to calculate this power? How to remember this power? Power factor is active power divided by apparent power. You just remember this. Power factor is active power divided by apparent power. We know that. Similarly, if you want to calculate the power factor, you will get this. You will get this. This is my power factor. But this power factor formula is again not true. This power factor formula is applicable only if the source is pure sinusoidal and the current has harmonics. If the current has harmonic and the source is a pure sine wave, then you require this formula. And in power electronics, these kind of situations are everywhere, where the voltage source is a pure sine wave and the current has harmonics. Let's discuss this formula. Let's say I have a situation. Let me proceed. Let me go to the next slide. Yes. Let's say I have a network. I have a power electronic network in which I have connected a source, VST. Let's say this is VST. And VST is pure sine wave. VST is pure sine wave. Let's say this is my VST. This is pure sine wave. Vm, this is minus Vm. 0, pi, 2 pi. And this is omega t. Okay. Now, let's say the current has harmonic. VST is a pure sine wave component. VST is a pure sine wave signal, and the current IST has harmonics. Let's say the current is a square wave. Let's say the current is something like that. It's a square wave. Current is a square wave. Okay. Now, if the current has square wave, and let's say this current is I naught, this value is, let's take maybe, let's call it I naught, and this is minus I naught, 0, pi, 2 pi. Now if we want to calculate the power factor, input power factor, then how to calculate that? Okay, let me tell you guys. Now, since the source has pure sine wave, the source voltage has pure sine wave, and the source current is not pure sine wave, you can apply this formula. There is no problem. No problem at all. If you remember this formula, there is no problem. You can apply this formula. Otherwise, don't remember this formula. I always remember this: active power divided by apparent power. I always apply this formula. How to apply this formula here? Active divided by apparent, because we know that the input power factor is always active upon apparent. How to calculate the active power and apparent power here in this situation? Let's first calculate the active power. The active power. How to calculate the active power? It's very simple, guys. We know that this is a pure square wave. If the signal is a pure square wave, then we know the harmonic component. You have to remember the harmonic component of this signal, IST. If you need to write this IST, it will be equal to summation of 4I0 upon n pi. You have to remember this because you will encounter it many places. 4I0 upon n pi sine of n omega naught t. N from 1 to infinity, n is odd. So it contains odd harmonic sine terms. And this is the expression for IST. You have to remember this square wave. Whenever you encounter this square wave, you have to remember this. This is the IST. Now, if I open this IST, if I put n equal to 1 and 3 and 5 and 7, because n is odd, so IST will look like, IST will be equal to, let's put n equal to 1. So it will be 4I0 upon pi sine of omega naught t plus 4I0 upon 3 pi sine of 3 omega naught t, and there will be higher harmonics. This will be my IST. Now look, the voltage source VST. VST is Vm sine omega t. VST is Vm sine omega t. Okay, VST is pure sine wave. But the current has sinusoidal term, third harmonic, fifth harmonic, seventh harmonic. There are so many harmonics in the current signal. Now I want to calculate the active power. I also told you about the active power. Active power is, you can calculate active power using Percival relation. So let's calculate the active power now. So active power is, this signal do not have DC component, and this signal also it does not have a DC component. So you can say that the active power due to DC component is 0. Now it has omega naught frequency term, and it also has omega naught frequency term. So these two terms will participate in active power. Now the active power will be equal to VST RMS. Active power will be equal to 1 by 2 into Vm, 1 by 2 into Vm into 4I0 by pi cos of theta v minus theta I. Here theta v is 0 and theta I is also 0. So cos 0. This is my active power. Okay, this much of what is my active power. Now what is apparent power? What is apparent power? So apparent power is VST RMS is Vm by root 2, VST RMS Vm by root 2 into RMS value of IST. IST RMS is I naught itself. If you need to calculate the RMS value of this IST is I naught. So we have active power, we have apparent power. Let's take the ratio. If I take the ratio, we'll calculate the input power. We'll find the input power. So input power factor will be equal to Vm into 4I0 by pi cos 0. And if I break this 2 like this, 4I0 by pi root 2 cos 0 divide by, this is my active power. I have broken this 2 in two parts, root 2 and root 2. Okay, I have separated this two like this. Divide by the apparent power. Apparent power is Vm by root 2 into I naught. I naught is the RMS value of the source current. So you can see that this is cancelled. If it is cancelled, now what is the remaining part? This is the remaining part. This is my input power factor, and you can calculate this value. But before calculating this value, try to look at this. What is this? This is the RMS value of the fundamental component of this IST. This is the max value of the fundamental component. If I divide with root 2, it will be the RMS value of the fundamental component. So you can say that it is IS1. IS1 is the RMS value of the fundamental component. What is this IS1? IS1 is this. Yes, it is the RMS value of the fundamental component. Divide by the RMS value of the source current, IST. Divide by the RMS value of the total IST. Let's call it capital IS. This is the RMS value of the entire source current into cos of theta V1 minus theta I1. Theta V1 minus theta I1. 0. 0 is cos of theta V1 minus theta I1. The voltage angle is 0 and the current angle is 0. This is my power factor. But why to remember this formula? You can directly apply the same active power divided by apparent power and you can calculate the formula. You can calculate the input power factor. What is the problem? Why should I remember this formula? But we can say that the input power factor is this. This is applicable only if the source has pure sinusoidal term. If the source has higher harmonics, let's say triple frequency component, and further there are more harmonics, third and fifth and seventh, then you cannot apply this formula. Then you have to come to this active power divided by apparent power only. Okay, that's why I'll not recommend that you should remember this formula. And what is this displacement factor? This displacement factor is cosine of theta V1 minus theta I1. It means for displacement factor, what you need to do is you need to look at the fundamental component of the voltage and the fundamental component of the current and take the angle difference and take the cosine of that. We will call it displacement power factor. We'll call this term as displacement power factor. But again, the displacement power factor is true only when the voltage source is a pure sine wave component. Otherwise, if there are harmonics, let's say in this question, voltage has harmonic, current has harmonic, you cannot find displacement factor here. There is no meaning of displacement factor. Okay, you have to be careful. You have to be careful in this situation. Displacement factor, displacement power factor, you can say, it is the cos phi 1. It means you can say that it is cos of theta V1 minus theta I1. So it is the cosine of the angle difference of fundamental voltage and the fundamental current. But this is valid only if the source has pure sinusoidal term. If the source has harmonics, then there is no meaning of displacement power factor. Okay, so you have to be careful. These things are defined only for particular situation. You cannot mix them. You cannot say that this is applicable everywhere. This is applicable everywhere. Yes, this is true. That's why I not recommend this formula. But there are some questions in which they will ask you about displacement power factor. Let's say I take a different situation. Let's say I have an electrical network in which I apply a voltage source VST. VST is a pure sine wave. VST is a pure sine wave. Let's say this is my voltage source VST. 0, pi, 2 pi and 3 pi. Okay, this is omega t. Now let's say the current is a square wave, but it is like this. Let's say this is alpha. This is alpha and here is pi. Here it is pi plus alpha. Okay, let's say the current is like this. Let's say the current is a square wave and it is like this. Now the current is like this. Now, what is the displacement power factor? Here we can calculate the displacement power factor. How to calculate the displacement power factor? It's very easy. To calculate the displacement power factor, since the voltage source has pure sine wave and the current has harmonic, we can calculate the displacement power factor is cosine of theta V1 minus theta I1. It means it is the cosine of angle difference of fundamental component of the voltage and the fundamental component of the current. Now, if you draw the fundamental component of the current, you can see that the fundamental component of the current will be like this. This is my fundamental component of the current. And the fundamental of the component of the current will lag the zero crossing of this current will lag by alpha. And the fundamental component of voltage is starting from 0, and the fundamental component of current is lagging by alpha. So you can say that displacement power factor is cos alpha. This is my displacement power factor. Okay. This displacement power factor will become true power factor only if this network is linear. Only if this network is linear. Let's say this is the fundamental sinusoidal source. The source is a pure sine wave. And this network is linear. Linear means this network contains RLC. It has no thyristor component or diode component. It does not have any non-linear elements. If the network is linear and the source is a pure sine wave, then this displacement power factor will be equal to the true power factor. And we have done this in network theory. In network theory, if you remember how to calculate the power factor. In network theory, the power factor is equal to cos of theta v minus theta I. You just apply this formula. And this is equal to true power factor. But in power electronics, the true power factor is not this. This is the displacement power factor. Because in power electronics, we have some non-linear component which are connected in the network. That's why the current will have some harmonics. Even if the source voltage has pure sine wave, the current has harmonics. If the current has harmonic, then the true power factor will not be equal to this theta v minus theta I. It will be called displacement power factor. Okay. So now we understood that if power factor is poor, it doesn't mean that the power factor is poor due to inductive load. There are some situations in which power factor is poor due to power electronic converters. Power electronic converters are also responsible for poor power factor. Because due to power electronics converter, what we have is voltage source is pure sine wave, but the current is not pure sine wave. Current has harmonics. And because of those harmonics, power factor will be poor. Okay, the true power factor will be poor. I hope you understood it. So remember this point. Power factor poor doesn't mean that load is inductive or load is capacitive. It might be possible that load is purely resistive, but there are some power electronic converter. Which are connected in the circuit. Those are responsible. So it is very important. And if the power factor is poor, let me tell you one more information. If the power factor is poor due to power electronics converters, then you cannot improve the power factor using the capacitor bank. Okay, you have to remember like this. If the power factor is poor due to harmonic component, due to harmonics, if the power factor is poor, in this case the power factor is poor. What is the power factor? The power factor will be equal to IS1 over IS into cos of alpha. This is my power factor. In this situation, let's say the voltage is like this and current is like this. Then the power factor will be this, IS1 over IS. What is this IS? IS is the RMS value of this entire current. And what is IS1? IS1 is the RMS value of this fundamental component. So take the ratio of this and cos of theta V1 minus theta. This is my power factor. And this power factor will be poor. So this power factor is poor not because of load is inductive or capacitive, or it might be possible that the load is maybe resistive or maybe whatever, RL type of load. Not resistive, you cannot say, but it's a different type of load, you can say. So power electronics converter are responsible for poor power factor now. So if you have to improve the power factor, you cannot apply capacitor bank here. Or you can apply this capacitor bank and try to improve the power factor. It will be even you are making the things difficult even. Okay, this will not work. So be careful about this. This is very important thing. So I hope you understood this point. So I told you about the input power factor, how to calculate the input power factor, and where this formula is applicable. This formula is not applicable everywhere. This formula is applicable only if the voltage signal, the voltage source is a pure sine wave and the current has harmonics. Then only this formula is applicable. Okay. Okay. Now let's come to the next thing, that is inductor and capacitor. In inductor and capacitor, I think everyone know about inductor and capacitor. But be careful, in inductor and capacitor, we know that LdI by dt is equal to VLT, and so if somebody will provide you the wave shape of IT, you can plot the wave shape of VLT. There is no problem. Okay. But this relation will tell you many things. Now what this relation will tell us, if IT has maxima, at maxima point VLT is 0. It means whenever current has maxima, at that point VLT is 0 and vice versa. It means if the inductor has 0 voltage instantaneously, let's say at some instant voltage across inductor is 0. At that instant, you will have the maxima of the current or minima of the current. Maxima or minima. Generally, you have maxima in power electronics. So, what I can say is, again, let me repeat. If the voltage across inductor is 0 at some instant, let's say, voltage is varying, but at some instant, let's say voltage is 0. If the voltage is 0, it means the current has the maxima. But the voltage is not 0 for continuous time. I mean, it is not constantly 0. I mean, continuously it is not 0. It is 0 for some instant. It means the voltage is like this. If the voltage is varying like this, you can see that at this instant or this instant or this instant, voltage is 0 for some instant, for just small instant. So you can say that at those instants, the current will have the maxima or minima point. I hope you understood this. During this, according to this differentiation relation, you can say like this. There is one more thing that you can tell. If you invert this relation, this differentiation relation, if you invert this, then what will you get? What will you get is, let me write, where should I write it? Okay, let's take dt on this side. So IT will be equal to I0, I'm writing directly, 1 by L VLT dt 0 to t. Okay, and this is my IT. Because I'm starting from 0, that's why I have to take initial current I0. If I'm starting from t naught, I have to take IT naught. So while inverting the differentiation relation, you have to be careful that you have to write the initial value also. Because there are some students who think that inverse of differentiation is integration. So they think that this is the only part that will come. It is not correct. Actually, since you are starting from 0, you are looking at 0 time, so you have to place the I0 part also. Okay, so this is the inversion of this relation. Now, using this relation, what I can say is, I'm not going to the basic thing, I'm going to revise you and I'm just telling you the information. So if you don't know that information, please go to your notes and please revise that. So according to this relation, what I can say is, I can say that if current is periodic in the inductor, if current is periodic through this inductor, then the average voltage across this inductor will be 0 and vice versa. Okay, let me repeat this statement again. If the current is periodic, if the current through the inductor is periodic, then the voltage average value or average voltage or the DC voltage across this inductor will be 0. Okay, so be careful. It is very powerful statement. Okay. Now, where you are going to encounter this situation? Everywhere in power electronics, everywhere. In power electronics, you will have steady state. In any circuit, if you have steady state, and in that circuit, if the load is some inductive load, let's say some RL load, or maybe there is some inductor. There is some inductor in the load. And you are analyzing the circuit under steady state. Under steady state means the current is periodic. The current through the inductor is periodic. In power electronics, you remember this statement. If there is a steady state, and the load has some inductor, then you can say that the current through the inductor will be periodic. And if the current through the inductor is periodic, the average voltage across this inductor will be 0. Okay. Now you will ask me, sir, where I'm going to encounter this situation. Okay, let me tell you. Let me tell you where you are going to encounter this situation. Let's say you have RL load. You have RL load. And you have thyristors. You have thyristors. In phase control rectifier, you have thyristors like this. Okay. You have thyristor. And there is some source connected here. Okay. Now, let's say the current is flowing, I naught T, and the circuit is under steady state. If the circuit is under steady state, what is the meaning of this? The meaning of this is the current is periodic. Steady state means everything which is repeating again and again. This is the meaning of steady state. If something is increasing, if something is rising, it means it will not reach steady state. Steady state means, I mean, it's repeating nature. We call it steady state, okay? So if the circuit is under steady state, it means this current is periodic. If the current is periodic, then the voltage across inductor, the average voltage across inductor, VLT average will be 0. VLT average will be 0. So whatever the output average is, that output average will always be equal to the VRT average. So you can say that V0T average will be equal to VRT average. So you have to be careful. You have to be careful about this statement. This is very powerful statement, guys. This is very powerful statement. Okay, let me repeat this again. If the current through the inductor is periodic, then the average voltage across inductor will be 0 and vice versa. If the average voltage across inductor is 0, then the current will be periodic. Now, you will encounter this statement in DC-DC converter also. Let's say we have a buck converter. Let's say I have a buck converter, DC-DC converter. In DC-DC converter, we have inductor in every type of inductor, in buck converter, boost converter or buck boost converter. We have inductor. And we know that this circuit is working under steady state. So under steady state, we know that this current is periodic. This ILT is periodic. Then only it will reach steady state. So if this ILT is periodic, then we know that this VLT average must be 0. VLT average must be 0. So what we do is to find the relation between this supply voltage and this output voltage. If you need to find the relation between the supply voltage and the output voltage, what you need to do is you just plot the voltage signal. You just plot the wave shape of VLT. If the wave shape of this VLT is plotted, you just put the average value equal to 0. And you will get the relation of output voltage and the input voltage. There is no problem. It's very simple. Okay. So you have to remember this inductor properties. You have to remember this inductor properties. Okay. I hope you understood this. So this was the inductor relation. Similarly, the capacitor. This is the difference. I mean, if voltage is given to you, you can calculate the current. From this relation, you can always write VCT. VCT is equal to VC0 plus 1 by C integration 0 to T IT dt. It means in inductor, this was the relation. In capacitor, this is the relation. So you can interchange the voltage and current. Everything is simple. Everything is same. In inductor, what I was saying, if the current through the inductor is periodic, then the average voltage will be 0. In capacitor, what should I say is, if the capacitor voltage is periodic, then the average current through the capacitor will be 0. It means if the capacitor voltage is periodic, if the capacitor voltage is changing periodically, then there will be no DC component through the capacitor. There will be no average component of the capacitor. Average current of the capacitor will be 0. Now, look at this situation. Look at this situation. Here, the output voltage is like this. This is the average value of the output voltage, but actually the output voltage is fluctuating. Actually, output voltage has ripples. This is my output voltage, which is changing with time. So if output voltage is changing with time and it is fluctuating like this, but it is periodic. So if it is periodic, what you can say is, you can say that the DC component of the current, ICT average will be 0. ICT average will be 0 because the voltage across the capacitor, the output voltage is periodic. If the voltage across the capacitor is periodic, average current will be 0. It means there will be no DC current through this capacitor. Whatever current we have in this circuit, ILT, the average value of this ILT will not go through this capacitor, it will go in the resistor. Okay, so you have to be careful at this situation, at this case. Okay, so this is again very important, guys. This is very important statement. So you have to be careful about capacitor and inductor. I hope you understood these statements, and I hope you know these statements. Okay, now let's proceed. Now we have, so this was some kind of basics that you should know in power electronics. It's a bit revision, but there are so many things that I can't revise, but I'm telling you those important things. Okay, so I hope you are enjoying. Tell me, guys, are you understanding these? I mean, are you getting these points? Tell me, everyone. You are not replying. The chat section is when you are very silent. Tell me everyone, are you getting these points? Tell me. You're not replying here. It's a bad habit. It's a bad thing. You should reply. Okay. Okay. Now let's proceed. Now we have effect of source inductance in diode circuit. So first of all, we will discuss about diode circuits. So we have this diode circuit and we have this constant current source, and there is some source inductance, and there is a Vm sin omega t sinusoidal voltage source. So in case of this sinusoidal voltage source, you have some overlapping period. Because of this source inductance, you have some overlapping period. If there were no source inductance, then you can say that whenever this is positive, this diode will conduct. Whenever this is negative, this freewheeling diode will conduct. So there will be abrupt change of current. Abrupt change of current here. If you need to draw the source current, if there is no source inductance, then the current will be like this. This will be the source current, 0 to pi and 2 pi and 3 pi. If you don't know how this came, how this came, you have to revise this topic. Okay. So this is the basic of the source inductance, effect of source inductance. So now, if you don't have the source inductance, then whenever this side voltage is positive, because these two diodes will be under common cathode configuration. If the source inductance is not there, if it is sorted, then, and let's assume that this is 0 volt. So you can say that this, if this is 0 volt, this is VST now. This is VST, this is 0. So these two diodes are under common cathode configuration. Their cathode is common, and the anode of this is connected at VST, anode of this is connected at 0 volt. So in common cathode configuration, which diode will conduct is the diode which has the highest voltage on its anode. The diode which has the highest voltage on its anode will conduct. So now look, we have the pure sinusoidal voltage. The voltage is like this. The voltage is like this, 0 and then pi and then 2 pi. So the voltage is like this. So from 0 to pi, this voltage is higher than 0. This is 0 and this is positive. So you can say that this diode will conduct. It means the entire current will flow through the source. Whenever this voltage is going to be negative, whenever this VST is negative, whenever this is negative, what will happen is, if the voltage is negative, then this point is negative, this is 0. Now the 0 is higher than negative value. It means now the freewheeling diode will conduct. It means the current will circulate here, and there will be 0 current through the source. Okay. So you can say that during this positive interval, this D will conduct, and during this negative interval, this FD will conduct, freewheeling diode will conduct. Okay. So if you try to look at the output voltage, whenever this diode conducts, this VST will appear here and this 0 is appear here. So you can say that the output voltage is VST whenever this diode is conducting. Whenever this diode is conducting, the output voltage will be same as supply voltage, same as VST. And whenever this freewheeling diode is conducting, output voltage will be 0. It will be sorted and output voltage will be 0. So if you draw the output voltage, output voltage will be like this, 0 and pi, and then from pi to 2 pi it will be 0, and then from 2 pi to 3 pi it will be like this. So this will be my output voltage, and you can calculate the average value of this output voltage. There is no problem at all. Okay. But the problem is when we have the source inductance. If we have this inductance, then what will happen is current cannot change abruptly. This source current cannot change abruptly, and it will not go to 0 abruptly. Okay. So there will be some overlapping. So before 0, what was there? Before 0, let's say freewheeling diode was conducting, and there is no current in this diode. Let's say before 0, the voltage was negative. Because the voltage was negative, that's why the freewheeling diode was conducting. So the entire current was flowing like this. Okay. And the output voltage was 0. Now what will happen is, at t equal to 0, this become positive. If it become positive, then this current should flow through this diode, but it will not be transferred to this diode abruptly because we have the inductor, we have the inductance. Because of this inductance, this current will increase slowly and this current will decrease slowly because the total current should remain constant. No? So what will happen is, for some time, for some mu interval, for some time, for some small time, this diode and this diode both will conduct. This diode and this diode both will conduct. This current will try to decrease and this current will try to increase. It will not increase abruptly because of this source inductance. What will happen is, the source current will go like this and it will become constant and it will take some time, mu. It will take some time, mu. Similarly, the freewheeling diode current, what will happen to the freewheeling diode current? It will decrease to 0. The freewheeling diode current will decrease to 0 in this mu interval. Okay. So you can say that both diode will conduct. If both diode are conducting during this mu interval, the output voltage will be 0 because this freewheeling is also conducting now. So during this interval, the output voltage will be 0. You cannot say that the output voltage will be same as VST. So there will be some less in the average output voltage. The output voltage wave shape will be like this. From 0 to mu, there is overlapping. If there is overlapping, voltage is 0. This freewheeling diode is conducting, this diode is conducting. So there is, you can say there is some overlapping. Output voltage is 0. From mu to pi, you can say that the entire current is flowing through this inductor. And this is sorted, and since constant current is flowing through this inductor, voltage across inductor is 0. Since current is constant, the voltage across this inductor is 0. So whatever this source voltage is, the same voltage will appear here. So you can say that from mu to pi, the voltage will be like this. So there will be a decrease in voltage. There will be a decrease in voltage. Average voltage will get decreased. Okay. Now, if you want to calculate the mu, how to calculate? You have to calculate, you have to apply the KVL in this loop. When there was overlapping, during that overlapping interval, you just apply the KVL in this loop, and using KVL, you will find that cos mu equal to 1 minus, here you have minus. Let me correct this. So it is 1 minus, just a minute. Yeah, it is 1 minus omega naught ls I naught by Vm. I mean, I have written this formula only, but you can check this formula. It's very important formula, guys. It's very important. So you have to be careful about this. Effect of source inductance. This is a simple circuit. In this simple circuit, this is my mu. You can calculate the mu from here, and then you can calculate the average output voltage. There is no problem, I think. Okay. So please revise this concept. It's very important. Now let's come to the full bridge. You can say the bridge rectifier, and there is a current source here. So again, we have the source inductance. Due to this source inductance, the source current will not change abruptly. If there is no source inductance, what will happen is, this current will flow through D1, D2 first, 0 to pi, it will flow through D1, D2, and from pi to 2 pi, it will flow through D3, D4. So the source current will change abruptly like this. If this is the source voltage, the source current will be like this. If there is no source inductance, from 0 to pi, it will be positive. From pi to 2 pi, it will be negative. Okay, so it will be like this. It will be like this. The source current will be like this. It will change abruptly. But because of this source inductance, what will happen is, there will be some interval in which all the diodes will conduct. All the diodes will conduct. Okay, and that interval we call as overlapping interval. During that interval, output voltage will be 0. Okay, output voltage will be 0. So how to calculate that interval? Again, KVL, KCL. You have to apply KVL in this loop. Okay, and you can say in this loop, in either loop, you have to apply the KVL. Okay, you please revise this concept. It is very important. So if you apply the KVL, what you'll get is, you'll get cos mu is equal to 1 minus, here in single diode case, 1 minus omega naught ls I naught by Vm. But here we have 2 omega naught ls I naught by Vm. Okay, now this will be the mu formula. From here you can calculate the mu. If mu is known to us, then the average output voltage will be like this. Now what is this? Look, if there was no source inductance, the average output voltage shape will be like this. Average output voltage shape will be like this. And the average value of this output voltage will be 2 Vm by pi. This is the wave shape of V naught t, not average voltage. It is the wave shape of output voltage. Output voltage will look like this if there is no source inductance. But if there is a source inductance, then what will happen is this 2 Vm by pi will be reduced by this factor. Okay, due to this source inductance, this will be reduced by this factor, and the shape of the average output voltage will also be changed. I mean, during this interval, it will be 0 because for all the 4 diodes are conducting. Similarly, during this interval, all the 4 diodes are conducting. During this interval, all the 4 diodes are conducting. So the average value is decreased. During this interval, output voltage is 0. If I need to plot the output voltage will look like this. During this mu interval, output voltage will be 0. So you can say that average value is decreased. 2 Vm by pi was the previous average value when there was no source inductance. But if there is a source inductance, then 2 Vm by pi minus 2 omega naught Ls by. But this formula is valid only if this source is a sinusoidal source. If source is Vm sin omega t. If source is a triangular wave or square wave, then this formula will not be applicable. Okay, so you have to be careful, guys. You have to be careful. These formulas are not applicable everywhere. Okay, so you have to be careful. These formulas are applicable only if the source is a sinusoidal source. Then only you can apply this. I'm telling you the process also, how to calculate these, how to come to these formulas. I'm also telling you the process, okay, because process is important than the answers. Now we have the 3-phase circuit. In 3-phase circuit, again, look, cos mu will be equal to, how to calculate the mu interval, because source has some inductances. So cos mu will be 1 minus 2 omega naught Ls by root 3 Vm. This is line voltage. So you can also replace it with line voltage. So there is a similarity in formulas. Cos mu 1 minus, in single diode case, there was only one was there. Na? Now we have 2. In bridge rectifier, we have 2 omega naught Ls I naught by Vm. But now we have 2 omega naught Ls I naught by VL. In place of Vm, because in 3-phase we have line voltage. That's why root 3 Vm is used. Okay. This way you can remember this formula. But again, this formula is applicable only if the sources are pure sinusoidal. Vm sin omega t. A phase is Vm sin omega t and B phase is Vm sin omega t minus 120 and C phase is Vm sin omega t plus 120. Then only you can apply this formula. If the source is a triangular wave or square wave, then this formula will not be applicable. Okay. So you have to be careful, guys. You have to be careful. I hope you understood this point. Okay. Now, this way you can calculate the mu. Now, how to calculate the average output voltage? Let me tell you. If there is no source inductance, the average output voltage will be equal to V naught T average will be equal to 3 root 3 Vm by pi. This will be the average output voltage if there is no source inductance. But due to source inductance, this average will be reduced and reduced by 3 omega naught Ls I naught by pi. In bridge rectifier, it was 2 omega naught Ls I naught by pi. Here you have 3 omega naught Ls I naught by pi. Okay. So you have to be careful how much voltage is reduced, how much average voltage is reduced. Remember, this is not phase controlled rectifier. These are diodes. 3-phase uncontrolled rectifier is there. Okay. So in 3-phase uncontrolled rectifier, I am discussing about effect of source inductance. I hope you understood it. And these formulas are very, you can say, similar formulas. You can remember, you can make a table. You can make a table of these formulas and you can remember these formulas. I hope it is clear to everyone. Now, let's come to phase controlled rectifier. In phase controlled rectifier, it may be single phase or 3-phase. We have 2-quadrant operation. What is this 2-quadrant operation? We can take this voltage as positive and this current as positive. It means this load is absorbing power. Here if I connect a load, across this load we can achieve positive voltage and positive current. It means this load can absorb the power. We can operate in first quadrant. And there is one more thing. In phase control rectifier, we can change the polarity of the voltage, not the current. Current cannot be changed. So current remains same, but the voltage can be negative. If the voltage is negative, if the voltage polarity is somehow changed and the current remains same, then this will deliver the power. So it's kind of from the load side to the source side. The power is flowing from the load side to the source side. So there is an inversion. You can say we have 2 type of operation, 2-quadrant operation we can take. But to get this inversion possible, we must have some source in the load. there must be some source there must be some kind of source that should be connected in this load. So it is possible if there is some source in the load. Let's say some load is RLE type of load. Let's say the load is RLE. So in this type of load, we can change the power flow. We can invert the power flow. If somehow we can manipulate this E, okay, then we can invert the power flow. So in single phase or three phase converter controlled rectifiers, what we can do is we can do the power flow from AC to the load side. We call it rectification, from AC to DC, or we also go from DC to AC. Okay, from AC to DC and DC to AC, both are possible. That's why it's a two quadrant operation we can get from this. Okay, so I hope you understood it. Now there are many type of single phase controlled rectifier with different type of load. Let's say the load is R load, L load, RL load, RLE load. So LE load, RE load. So there are many type of load. Okay, the load can be resistive, load can be purely inductive, load can be RL, load can be LE, load can be RE, load can be RLE, okay, and load can be RLE with E opposite polarity. So there are so many type of loads. Okay, and there is current source, constant current source. Okay, I mean there are so many situations. These type of loads are possible. You have to understand everyone. If the load is R load, what will happen? If the load is L load, if the load is RL load, and in every situation, there is a boundary. There is a boundary between continuous conduction and discontinuous conduction. Continuous conduction and discontinuous conduction. Between continuous and discontinuous conduction, there is a boundary. There is some firing angle alpha. There is some firing angle alpha at which the conduction is just continuous. At which the conduction, it means the current, output current, I naught T. There is some firing angle alpha in the, let's say there is a single phase full wave controlled rectifier. We have single phase full wave controlled rectifier. Let's say we have this circuit. And we have the source, and here we have connect some load. So it is a single phase full wave controlled rectifier. Now, in this case, there is some firing, load can be R load or L load or RL load, whatever. In every situation, we have some alpha JC. JC means just continuous, just continuous. It means we have to find this alpha. If the actual firing angle is less than this alpha JC, then the conduction will be continuous. Conduction will be continuous. Continuous conduction. Continuous conduction. And in continuous conduction, V naught T average will always be 2 Vm by pi cos alpha. Remember this. In single phase rectifier, okay, in single phase control rectifier, if conduction is continuous, average output voltage will always be 2 Vm by pi cos alpha. Okay, you have to be careful. You have to calculate that alpha JC. If you somehow you know how to calculate this alpha JC, it will be very easy. Now, in case of current source, let's say there is a current source here, then everything is gone. I mean, if there is a current source, then always the conduction will be continuous. There is no point of discontinuous conduction because the current source is connected. Now, if current source is connected, conduction will always be continuous. If conduction is always continuous, the average output voltage will always be like this. Okay, 2 Vm by pi cos alpha. It's very simple. The current source case is very simple. Okay, so you have to be careful about this case. Now, for other type of load, R load, RL load, L load, whatever, okay, there is some alpha JC which will exist. Okay, you have to calculate that alpha JC. There are methods by which you can calculate alpha JC. I'm not teaching those methods but you have to be careful about that. How to calculate this alpha JC, the boundary value, the boundary angle above which the conduction is discontinuous, below which the conduction is continuous. Okay. Now there are some things that I want to tell you. Let's say we have the load. Be careful, guys. Those are some points which you have to remember. Let's say we have some load, okay, and the load current I naught is discontinuous. Let's say the load current is discontinuous. In this phase control rectifier, if we connect some load and the load current is discontinuous, always remember that if load current is discontinuous, it must be periodic. It must be periodic all the time. Periodic always. It must be periodic always. Condition is it should be sinusoidal source. Okay. If the current is discontinuous, it must be periodic. This is the first point. Just remember this. Whenever the conduction is discontinuous, it will be periodic. The current will be periodic. Okay. The next point. The next point is, if the load contain resistance, if the load has resistance, then also the current will be periodic, whether it is continuous or discontinuous. Okay. I know T, it may be continuous or discontinuous. Continuous or discontinuous, whatever. Discontinuous. Continuous or discontinuous. It will always be periodic. It will always be periodic. Always be periodic. It will always be periodic. But if the load contain pure inductor, R is 0. If load does not contain any resistance is 0, L is non-zero. It has some L load. Some L is there. C, you just don't take C. Let's remove C, because we don't take such kind of loads in which the capacitor is there. Okay. So let's say the load is such that its resistance is 0. There is only inductance. It can be L load pure or LE load. Okay. So in pure L load or LE load, it might be possible that current is continuous and rising. Current is continuous and rising. It might be possible if the load is L load or LE load. But if some R came, if there is some non-zero R, if R came, then it must be periodic, always periodic, whether it is continuous or discontinuous, it doesn't matter. If R is there, it will always be periodic. Okay, you have to remember these points. But if the load is pure L or LE type of load, then it might be possible that current may be rising, or maybe rising and continuous, or it may be possible that current is discontinuous. It may be possible that current is discontinuous. If current is discontinuous, it will always be periodic. If current is discontinuous, it will always be periodic. Remember this point. Okay, so there are these points that you have to be careful, and in the next class I'll apply these points. Okay, in the next class I'll apply these points and we'll revise the phase control rectifier itself. Okay, because this is not over yet. Okay, this is not completed, the phase control rectifier, because I have only told you about the type of loads. Now I need to discuss these load one by one. Okay, and after that we'll go to the DC-DC converter. But there are not many formulas in power electronics. There are not so much formulas. If you try to understand those concepts, if you try to understand the wave shapes, okay, then you don't need any formula. Okay, so we'll discuss those effects, those loads in the next class, and we'll discuss effect of source inductance in controlled rectifier, and then we'll cover this DC-DC converter part also, and then inverter. Okay, so that's all for today's session, guys. I hope you liked this session. I hope you enjoyed. So I hope this session was very helpful for you. So please subscribe our channel and like this session if you have not liked it. So please like this session. It will be, I mean, if you like it, then it will reach to maximum students. And make sure that you you download our mobile app, BYJU'S Exam Prep. On this mobile app also, there are some free classes which are going on. There are some good educators which you can attend those classes and you can take advantage of those classes. Okay, so thank you for attending this class. Thank you for your patience, and I hope you enjoyed this session. So these type of sessions will come in upcoming days also. So tomorrow also we have this session. So on tomorrow we will discuss the remaining part. Okay, I hope you enjoyed. So that's all for today's session, guys. Take care and see you tomorrow. Thank you and take care. Bye.